Hello, good morning, good afternoon, and good evening. I'm Kaya Ozol from Primex, and I'm honored to be able to have a conversation today with Kevin MacDonald.
Hello.
And Kevin, we've worked together for quite a long time, Primex with you, and I'd be really interested in hearing more about your background and how you got interested in concrete, because people don't just fall into it. There's something that pulls them in.
Yes, that's true, and not just gravity. So I spent quite a bit of time with my dad, who is also a construction materials engineer. In fact, a professor at Ryerson Polytechnic University in Canada, and I ended up going to engineering school and studying chemical engineering, which is the art of taking the molecules we have, scrambling up the atoms and making the molecules that we need. And I got a part-time job or a summer job looking at bridge structures and their performance. And the problem with bridge structures and their performance in Canada is the corrosion of embedded reinforcing steel. So we get a lot of corrosion going on, and that corrosion causes the structures to prematurely deteriorate. And it came clear to me that the things that I was doing in chemical engineering school were the very issues that were being struggled with at all levels in looking at concrete durability: the movement of ions, movement of water, the electrochemical corrosion process. And so in order to study the corrosion of steel in concrete, you have to study the concrete part, the environment. And that's when it became very, very interesting. So in a way, you could say I inherited my interest in concrete. I remember as a very young child going down to the labs at Ryerson, probably to get out of my mother's hair so she could get something done, and thinking it was fascinating to see these materials that were being worked with. And they had a tank for curing concrete, as labs do, that had a film of something on the surface that you could move your finger across and cut into squares, and they would float around. You could cut your initials in. I know today that that's calcium carbonate that's made from carbon dioxide being pulled out of the air. Carbon dioxide, of course, in the 1970s, when I would have been down in my father's lab, we wouldn't have thought anything of it. But we now know that we can, there's quite a bit of interaction between carbon dioxide and concrete, and we can use concrete to absorb carbon dioxide from the atmosphere, as well as the production of concrete with Portland cement is responsible for, depending on whose numbers you look at, 4 or 5% of the CO2 emissions worldwide. Cement and concrete are things that we use on colossal scales. The only thing we use more than concrete is water. And so the study of concrete becomes interesting because it is ubiquitous. It's synonymous with our modern society. Our modern civilization would not exist.
Tell me more about how slabs on grade has changed or evolved in the past 50 years.
So if we go back 50 years ago, in the mid-1970s, concrete was made with Portland cement that was relatively coarsely ground, relatively slow setting because of the chemistry that was there. And those slabs could be placed and you would get a certain amount of strength. And so you would know how thick the slab would have to be so that when it bends, and it bends like that, right? So when it bends, you know how much tension is occurring down here. You make sure that it isn't going to crack. And that is related to that crushing or compressive strength. In the 1970s, we began to make faster setting cements. And we did that chemically by changing the relative proportion of A-lite and B-lite, which are a couple of chemicals inside the cement, by changing the relative fineness, by grinding the cement finer so it will react faster, and by using water-reducing admixtures that would allow the concrete to be more fluid than it would have been otherwise. And that's terrific. So now the concrete's easier to place, it gains strength faster, so you can make the slabs thinner. And it's setting quickly, so everyone can go home early. The problem is that those slabs also began to shrink more. The water-reducing admixtures increased the shrinkage. The changing chemistry increased the shrinkage. The fineness of the grind increased the water demand and indirectly indirectly increased the shrinkage. And it's probably worthwhile to just review shrinkage. So concrete made with Portland cement is, at the time of setting, has a defined length. And the minerals inside that are grown are made up of sheet after sheet of calcium silicate. As water evaporates from the concrete, the surface tension of the water, the same reason that you see the little rise in the water at the perimeter of a glass, pulls those sheets very little bit closer together. And each individual sheet moves hardly at all, but because you have billions of them, or trillions of them, you get some shrinkage. And we'll see somewhere around 400 or 500 microstrain, or 4 times 10 to the minus 4% shrinkage. So it doesn't sound like an awful lot, but that shrinkage sets up a stress. And that stress is no different than the stresses that are imposed on the structure by putting a load, a car, forklift, a chair, whatever else on them. In addition, because the amount of shrinkage is related to the amount of drying, at the top it gets shorter more than the bottom does, and it forms a curve. We refer to this as curling. Now there's some other funny things that go, and it isn't a perfect section of a circle, but what happens is that the slab can actually, that's sitting on the ground, can actually lift off above the ground. And now as a load comes across here, it does this, and eventually it will crack. And so we were having this terrible problems. The shrinkage causes cracking, and then it curls, and that curling causes cracking. And so a great deal of work was done. That then becomes the way you prevent this problem from occurring is moderate strength, moderate stiffness subgrade, tightly spaced joints. That is a solution, but it's not the only solution. And now as we move forward, we have other solutions that are present. And one of them is we can post-tension the slabs. So we cast the slab, and inside the slab at the time of casting are long wire ropes. And we take the wire rope and we pull it, and that shrinks pre-shrinks the concrete and puts it into compression, so that when the concrete shrinkage from those little layers of material comes back, the net effect is a slight compressive stress. So it won't crack, and so you can have very long joints. And those slabs, particularly the ones where we have been able to reduce the curling, can be thinner. And the reason they can be thinner is because that curling stress, remember the stress that's lifting it up, is the same as though you put a stress on and bent a beam or bent the slab. And so that gives you additional capacity. And if you have additional capacity, you can make the slab a little bit thinner. So there's been quite a bit of progress. There are still many people who say you have tightly spaced joints, moderate stiffness subgrade, moderate strength of your concrete, and you'll never have a problem. That's perfectly true. If you staple your trousers to yourself, they will not fall down. It works. Is it the best solution? It depends whether you're selling staples or whether you're having them applied. But it could be either way. But in many cases, there are other ways of solving engineering problems. And one of the dangers that we face as a society is when someone says, aha, I have it solved. I know exactly what to do. When we think we have the only solution, this is the way to do it, is usually a bad sign. It used to be when you go into a warehouse, you would walk around with a reflective vest, just like you're on the highway. And when the young lady driving the forklift was going to come around the corner, she'd honk so you would know she was coming. Today, you don't need a reflective vest because you don't need any light. As the robots that are running in there don't rely on light. They know where they are, X, Y, Z, because of the location, because of very accurate global positioning satellites. There are floors where humans do not go because the robots are moving around and the robots are saying, I'm over here, and the robot says, no, I'm over here, and so we'll make sure that our speeds match so that we don't crash, but the humans have no such emitters. And so if you're in these floors when they're running live, you are going to get struck by the robots that are not necessarily traveling in straight lines. They don't have to. If you take a look at some of these automated warehouses, they're absolutely fascinating. But you can't tell the robot, hey, over there's that section of slab that's curled up a little bit, so remember when you go over that, slow down a little bit so that you don't get launched. That really doesn't happen, but that you don't bump around and lose the load you're carrying.
I think this is almost a separate topic for the flooring, of course, and what has changed over the past 50 years. One of my questions in your explanation, what would you say these floors, it's not for, homes. You're talking about examples of for larger warehouses or logistical centers. It's not if I'm pouring a foundation in my home or my own driveway.
In a lot of cases, the slabs on grade that are being used where performance of flatness and thickness are important are in commercial warehouses, whether they're using as distribution facilities, whether they're being used for logistics transfer, whatever that they are. You can still build a driveway without a joint in it. And in many cases, we place a garage floor or a basement floor in a house and just let it crack. But the consequences of that are small. The consequences of uncontrolled cracking in a pavement, on a highway pavement, or in a distribution warehouse or a logistics warehouse, that's really where the innovation is occurring.
There is now an increased use of steel fibers in concrete. Mm-hmm. Can you explain how that improves concrete, or how does it set it apart from traditional concrete?
Sure, that's an excellent question. And we have seen a lot more fiber use in concrete, both steel and what they call synthetic fibers, although steel is a pretty synthetic material itself. So when we have steel fibers, we have a relationship between the fiber and the concrete where the fiber is much stiffer. It's much harder to pull and stretch it. The steel is much stiffer. We have a material where the steel is much stiffer than the concrete. So it takes a lot more force to get it to move the same amount of distance. And that's what we call a reinforcement. So as the amount of strain, as stretching of the material with the fibers and the concrete linked together intimately, we're going to get better stiffness, better resistance to that load. And that's what reinforcement is. And we've been making reinforced concrete since the 1880s. We use bars or we use mesh. And so those steel fibers allow a composite action to occur. So you get a material that is not the concrete and it's not the steel, it's a composite of their two. And we're very familiar with composites. Anybody who's ever used any fiberglass, which is a resin, which is brittle, with glass fibers in it. The glass fibers are stronger, so that you get something that has the properties of both the resin and the glass fibers. So steel fiber reinforced concrete has moved a great deal of the technology of making composite materials into our 2,000-year-old, 23,000-year-old material of concrete. And the steel and concrete allow plastic behavior as opposed to elastic behavior. When I say elastic behavior, if you have an elastic band and you pull on it, some people refer to that as as elastic behavior. But you can prove this to yourself. You just have to go to a restaurant. If you take a fork and wedge it in between two tables so that it's standing up, and if you push the fork and let it go, it will spring back. And that's in the elastic range. If you push the fork enough that you permanently bend it, it will only snap back a little bit. That plastic deformation means you've been able to carry a much higher loading than you were in the elastic range. Now, you can, again, same restaurant, in between the tables, wedge a plate, and you'll find that the plate has no elastic behavior at all. It will be imperceptible, and you push on it, and eventually it will go snap. You won't be asked back to the restaurant again, but you will have learned something about mechanics. And if we put steel fibers into concrete, we get that plastic behavior. We get strength after cracking. And that has made a huge difference. Our design codes in various places in the world recognize that to a more or lesser extent. Sometimes we have design codes that allow steel fibers to be used as a reinforcement. Sometimes we have design codes that say, well, that you can't count on it for reinforcement, but you can count on it for increasing the shear capacity or the cutting capacity, depending on where you are and what the codes are.
This is what I wanted to ask you about, because you mentioned, of course, ACI and codes which are developed by it. What about in other parts of the world? What about in Europe? What is similar to it? Which one has higher ranking? Which is more respected?
Well, they're equally respected in their areas. I've been a member of the Concrete Society in the United Kingdom since the 80s. It's a natural thing. My first two bosses and my PhD supervisor were English trained. And so the Concrete Society is similar to ACI in that they have committees and that they write documents. And one document that they write is TR34, which is a guide to construction and design of concrete floors, very relevant to our discussion here. So frequently what happens is, depending on what other country you're in, for example, if you're in Canada, you would use the ACI code, and the design code for slabs on grade is ACI 360. It may not be a design code. I think it may be a guide to design of slabs on grade. TR34, which is the publication of the Concrete Society, would be more commonly seen in a Commonwealth country, except Canada and the United States sharing a common border. That's less common. In South Africa or in India, or in most of the rest of the English-speaking world, you would see TR34 as the document that's looked at. And they're different documents. And this is what makes engineering design so fascinating, is though we're living in the same world, the design assumptions that are put into our guides and codes are sometimes different. They're based on tradition as well as being based on scientific application of sciences and mathematics. And so depending on where you are, but for the most part, those are the two you encounter. I looked at some slabs on grade many years ago for China, where TR34 was the code or the guide that they were using. So it very much depends. And because of the process of the way that they're written, they come out in new editions. And so it's not unusual for one to be ahead of the other and vice versa. The other aspect is the litigious nature of engineering societies, or the litigious nature of engineering in some societies versus others. And so where litigation is more common, the codes are more conservative.
And wouldn't you say that with the codes, one of the issues that that is stifling, possibly, maybe stifling is too harsh of a word, but for innovation, if we would compare it to the German car industry, which in the past 50 years, if you think how much cars have changed, it's night and day. But on many aspects with concrete, It does not. The innovation isn't there, or it's hard to come by.
It's a very good question, and part of it is the way in which systems are delivered. Let's pick a German car manufacturer, BMW, right? Bayerisch Motorwerk. So they make cars, but they don't make cars to someone else's design. Their manufacturing and their design are both in-house. And so their manufacturing and design people talk to one another. I know a little bit about the training of German engineers, and German engineers have some hands-on requirements before they can become professional engineers. In construction, at least in traditional construction, we still have a separation between the designer who executes a plan and the constructor or the installer who then puts that plan into practice. And as I said before, the contractor cares a lot about the plastic concrete properties. The designer does not. But the designer also, it may be in a situation where their design is put out onto the street for construction and they are not as heavily involved as they might want to be. And so they have to have the design constructible.
Is there any argument as to why, say, using mesh and rebar in concrete makes it stronger than steel fiber reinforced?
No, in fact it doesn't. I had a colleague of mine, a physics professor, tell me that if he liked, or if I liked, he would explain to me why the building code has the things in it that it does. And that was very nice of him to say, but I kind of chuckled because he can't, because we don't design concrete structures to be efficient. Sort of may come as a surprise, right? An engineer, someone who can do well for $1 what any idiot can do for $2, but we don't make our structures efficient because conventionally reinforced structures that are efficient fail by crushing the concrete, a sudden collapse without warning. We intentionally under-reinforce structures. We make the reinforcement less than optimum so that it will sag and deflect excessively. And that is one of the things that is not a scientific decision. That's an engineering decision. How are we going to manage the world? What's the structure going to look like at the end of its ability to resist, what we call an ultimate limit state? We've been able to design with steel fibers the same way you would design with individual bars or with mesh. Sometimes we have a concentrated force that we need extra bars to resist, or sometimes we have a concentrated force where we, in the event of a collapse, will want to arrest or stop a collapse from occurring. But you can make concrete just as strong with steel fiber as you can with individual bars.
Just as strong or stronger?
Well, you could make it stronger as well because you will get plastic deformation. And so, at the risk of really sounding nerdier than I am, because there's additional work that's required to stretch the steel fibers after the concrete is cracked. And so if you have conventional bars, those conventional bars also do that same amount of work. But because the bars in conventional reinforced concrete are intentionally placed where they are, if you have unexpected deformation, that the bars were not put in place at the time of casting, they're not there, but the steel fibers are everywhere.
Thank you. That was very explanatory, I think, for many as to the differences. All right, let's stop with that.